Okay, well, my apologies for all the rough start. We have new personnel, and I'm about to have a heart attack trying to get my tenure package put together. This has been the busiest 3 weeks of my life, so appreciate your patience. Soon things will be back to normal, and I'll have more time to get the new guys to do their parts. I think I see a better way of doing the videos, but for now, just take the lecture video as like audio, okay? You get the lecture notes, all right, and they're nice and sharp and clean, and so maybe just thumb through your notes while you're basically listening to the video, but at least it'll function in a way that, you know, you can see what I'm pointing at and saying, and you want a good clean thing to look at your lecture notes while you're listening to the videos. Okay, that's as good as we can do right now with all the constraints we have. Appreciate your patience. All right, let me just kind of move this around a little bit. And so how do I know which ones are ahead of which? Is red coming in first or is blue coming in first? Well, the easiest way to do it is all explained in this one little slide here that'll get scanned and posted. Say I have conventional fiber, which has 0 dispersion wavelength right here at 1.3 microns. Then just take a little walk, all right? Take a little walkabout. So say I above 1.3 microns, then step to the right. What happens to the D? D went up. Okay, here it's 0, here it's plus 10. So I step to the right, delta T goes up. So that means as I went towards the red, the longer wavelengths are going slower. Right? So the quick way to do it here is longer wavelengths. I took longer to get there, therefore the longer wavelengths, the red is going slower, so red will come in second. All right. Another way of saying that is blue comes in first. Blue leads the red. That's the so-called anomalous dispersion. I guess they just had to produce a fancy word because they were used to being below 1.3 microns, and that one they call blue. Okay, so just take a walkabout. We can go over this again more later when we talk about other things, but you can memorize it as, well, is D plus or is D minus, but then all of that changes when you go to dispersion compensating fiber, in which case the slope goes the other way. So I find it easier to just take a little walkabout. So say I'm below 1.3 microns, right? Take a step to the left. Now I'm headed towards the blue, right? So going towards the blue, the dispersion parameter got further away from 0. It doesn't matter to me, my way, I don't care that it's negative. It got bigger, right? Here's no dispersion, would be D equals 0. So as I go to blue, it's going slow, it's getting delayed more, so blue falls behind, so another way of saying that would be red leads the blue. Okay? Alrighty. How can I compensate for dispersion? Well, here's one way. It's called, oddly enough, dispersion compensating fiber. And it simply has a dispersion curve that slopes the other direction. This is a very busy figure here that has both the loss in dB per kilometer is this curve labeled on this axis, which you can see when you blow this up. The dispersion curve is the one I care about at the moment, and it looks like this, right? So this can cancel the dispersion that you have from other fibers. So I go through regular fiber. Say I went through 100 kilometers of regular fiber that had a dispersion parameter of 5, then my delta T is 5 times L times delta omega, right? If I have dispersion compensating fiber that slopes the other way, has a dispersion parameter of 100, then what do I need? What's the length of that I need? Well, I need 100 times some number giving me the same thing as I got up here. So I need a 5, right? 5 kilometers of dispersion compensating fiber would compensate for it. Again, we can go over these more slowly in person, but I wanted to go ahead and get these lectures out to you because some of you are in a panic about the homework. And so here's another way of doing it. I don't know that this one's on the homework, but I'll go ahead and throw this in here at the moment anyway. Is there a door there you can close? Or oh, okay, he's got his earphones on. I'm not sure when someone else is in the room. Okay, chirp fiber Bragg gratings, right? FBGs. A Bragg grating, let's start with that. Bragg grating just works like this, right? We have constructive interference for some wavelength based on the spacing between these scratches. These scratches work like mirrors, right? And so the wave comes down, hits the first one, bounces off, another wave comes down, hits the second one, bounces off. Then I'll get constructive interference at some particular color based on the spacing here between the scratches, right? Bragg saw that in scattering of electrons and crystals, but you can also see constructive interference, of course, just from, you've seen rainbow colors when you look down, if there's some oil that's spilled on top of a puddle of water, the oil actually rides on top of the water, so I get a bounce of the light wave off the oil, and then I also get a bounce of the light wave off of the oil-water interference. So when the thickness of the oil is just right, then some of those colors are going to be constructively interfered. Those are the colors I'm going to see. Right? Can you take a look at the camera and see that I'm here? Let's pause this now that